Good evening, College Trig. This is 8.4 vectors. In these notes, we got four main objectives. We got to make sure we are able to graph vectors. We got to make sure we can add and subtract vectors. And we got to be able to find magnitudes and scalar products of vectors and find unit vectors. If you've taken physics, a lot of this might be review. You might be able to zoom through this pretty quick, but we got to make sure together as a class we're on the same page here with vectors. So a vector has a magnitude and a direction. So the direction is usually an angular distance or northeast or something like that. So it'll be pointing in a direction, and magnitude is its length. Okay, so a thing to remember with vector is it has magnitude and it is direction. The arrowhead will be pointed in the direction of your vector. When adding two vectors, you can just simply do it by just joining them head to tail. So the head is where the arrow is pointed and the tail is at the end. So if I want to do the vector of A plus vector B, I have these, line them up, tip to tail, and the resulting vector is just the vector AB going from those 2 points. Notice it doesn't matter which order you add them, you get the same result. That if you did B plus A, you get the same vector in this direction, proving the commutative property for vectors. And notice that you can pick up vectors to add them tip to tail. So if you're just given these position vectors that are starting at the origin and you want to add A plus B, recognize that you can take this vector, line it up tip to tail, and you get the resulting vector R, which is A plus B. Same thing with the B vector. If you wanted to do B plus A, you can lay that tip to tail and you get the resulting vector, and the addition doesn't matter there as far as the order. So that is adding vectors there and graphing vectors. Okay, why do we ever need this? So lots of times in physics and different other applications, we have different forces acting upon an object. You might have a propeller. For this example, we have a propeller pushing you forward. Okay, and then you also will have another vector of wind pushing you in this direction. So the resulting of where the actual airplane ends up going is going to be affected by both the vectors, the force pushing it forward and the wind pushing it backwards along that point. So lots of different applications for vectors, and we'll look at a couple here tomorrow. So when we're subtracting vectors, so the subtraction of a vector, notice, is just a vector written in the opposite direction. So if this was the B vector originally, again, to subtract vectors, you just go ahead and switch the direction in a 180-degree manner. So if you want to add and subtract vectors, make sure you are lining things tip to tail. So on this diagram over here, you can see that A minus B, if this is your A vector and this is your B vector, and you wanted the resulting A minus B, you reverse the direction of B because it's negative, and you have negative B, line tip to tail, and this is the resulting vector, A minus B. We'll always bring back vectors back to the origin there. Okay, so that's subtracting our vectors. So how do we write vectors? So we have two choices, one using the I and J components, where I is your left and right, and your J is your up and down. You can also write it with these carets, and we know that this is not just a point 5, -6 because of the carets on the outside that informs us this is a vector. So when writing this out and drawing this, We know 5 is our left and right, so we go 1, 2, 3, 4, 5 here, and we go down 6, 1, 2, 3, 4, 5, 6, and then that vector is drawn from your origin, and it's in that direction. So we can see that this vector not only is going in a direction, but we also have a magnitude. It's no longer just a point. Make sure you're picking up on that. This is not equal to the point 5, -6 because it has a direction and magnitude to it. All right, so either choice for writing out a vector in the ij components or with your carets is appropriate. Position vectors between 2 points always reset at the origin. So to find these vectors, so notice we have position vectors 1 and 2. So we can see that 2.1, I have this vector to this smiley face. Okay, that vector I'm going to write in vector notation of my x component being -5, and my vertical component, my y component, is going to be 3. Okay, so for P2 is being represented by that point there, and that vector can be written as -2 and -4. So if we want a position vector, so if we're going from position 1 to position 2, we actually want this vector. So in order to do so, we have to take our x parameters minus our y parameters. So here we're going to take our negative x2, so -2 minus a -5, and our y components, -4 minus 3. And we see that this vector is actually going to be -2 plus 5 is going to be 3, and -4 minus 3 is -7. So that position vector, when we write it, it should be this vector in the green, and when we draw it, it should always be reset to the origin. So we see that is our position vector, how we move from position 1 to position 2. We could also write this as 3i minus 7j, be appropriate. All right, so then if we're adding vectors, notice we have 2 vectors here, I and v and w, and then we're going to have scalars. So in this context, our alpha here is a scalar. It's just any given number. So if we want to do v plus w, you add the I components, add the j components, and that's the resulting vector. For subtraction, you do the a components, subtract them, and subtract the j components as well. When you're doing a scalar, all you're doing is you're going to distribute the alpha through both to the I component and to the j component. You get a resulting vector as such. Last thing is magnitude, and magnitude, notice magnitude looks very similar to your Pythagorean theorem, because when we have a given vector and we have an a component and we have a given b component, to find the actual length of that vector is just your magnitude. And using your Pythagorean theorem to recognize we got a right triangle here as well. All right, so make sure you look over those. Here's an example working through here. I think addition is pretty straightforward. Just make sure with the subtraction of 2 vectors that this minus sign gets distributed over. So you have to do 3 minus -4, and you also have to do 2 minus 1. So that minus goes to both vectors, making sure you distribute that through. And then so that's some examples of addition and subtraction. Feel free to have those examples down in your notes and to be able to move forward from that. All right. So next what we have to do is we have to talk about the scalar. So if we have a vector m and we want to multiply it by 3, we can just go ahead and multiply each component by 3, and it's as simple as that. So if we're asked to do something like we are here in this example, what about 2v plus 3w? We can go ahead and do 2 times our v, which is 3, 2, and add that to our w vector, which is going to actually be 3w, which is -4, 1. And then I'm going to add them together and group them. So 2 times 3 is 6, plus my I component over here, 3 times -4 is -12. And then we have our j component, which is going to be 4. And for this one, we have plus 3. So then we got our resulting vector is going to be -6, 7. Okay, so a scalar is just multiplying it and increasing that magnitude. So here's an example to find magnitude. So we have the vector here that is 3, 2. The magnitude is just the length of that. So we can see this is 3, that's 2. So we do 3 squared plus 2 squared, square rooted, is equal to the magnitude of v. So then we get the magnitude of v is equal to the square root of 9 plus 4, which is equal to the square root of 13. We'll just leave it as that. Again, very similar to finding magnitude of complex numbers and absolute values there using our Pythagorean theorem. All right. So the last thing we have to talk about here is the unit vector. So what we want to do is we want to just be able to find a vector in the same direction, in the same as our original vector, but we want it if just 1 unit long. And that's going to be used a lot in physics so that the magnitude is always 1. So quite easily, if you just divide it by how long your original vector is, you will find your unit vector. Okay. So if this was our vector v, we're trying to find a single unit vector in the same direction that is exactly 1 unit long. So an example of walking through this here. So first thing I have to do is I have to calculate my magnitude. So I have 3 squared plus -5 squared square rooted. So I have square root of 9 plus 25, which equals a square root of 34. Okay, so then what I want to do is I just write, this is a scalar, and I divide this through, so I have 3 divided by the square root of 34, I. Remember, this I is not the imaginary I minus 5 over the square root of 34, j. I'm going to write this as 3 over square root of 34 minus 5 over the square root of 34. So we can check and verify that this is indeed a 1-unit magnitude vector by finding the magnitude of this, of our unit vector. So then we can do 3 over square root of 34 squared plus negative 5 over square root 34 squared square rooted. Well, I get 3 squared is 9 over the square root of 34. We already got a common denominator, because if we square both of them, it's 34. And we have 9 plus 25, square root of this. We get the square root of something over itself, which is the square root of 1, which is equal to 1. So we have verified that this is indeed a unit vector. That concludes our notes for tonight. Make sure you have them down for tomorrow, and we'll have an activity working with vectors.